Hello students, welcome back to another video lecture for ComSci 125 operating systems. So we're now moving to chapter 3, processes, and this will be an interesting chapter because we're going to learn about the ways in which the CPU executes programs. Okay. For the outline of this chapter, we're going to talk about the concept of a process, the abstraction of the process. Process is scheduling, operations of processes, inter-process communication, because processes might communicate with each other. There are two approaches to doing inter-process communication. We have shared memory and message passing. Some examples of IPC mechanisms and communications in client-server systems. Objectives for the chapter are the following. You should be able to identify the separate components of a process and illustrate how they are represented and scheduled in an operating system. So there is a representation of a process and there is a scheduling of processes in an operating system. Second, you should be able to describe how processes are created and terminated in an operating system, including developing programs using appropriate system calls to perform these operations. In your lab for this week, we have the Linux Process API lab. This is what you're going to do, or what you're going to accomplish. The third objective, you should be able to describe and contrast inter-process communication using either shared memory or message passing. Next, you should be able to design a program that uses pipes and Unix or POSIX shared memory to perform inter-process communication. An example of this using pipes is ls-l, then you have a vertical bar wc-l. This one here is a pipe. You have two processes, ls and wc, they communicate. Okay. Then client-server communication. This should be done in ComSci 137, but we'll have an overview of this in this chapter. And this lab is how to design Linux kernel modules. I don't know if we will be able to cover this, but we'll see. Okay, let's start with the process concept. So you've been interacting with an operating system for a long time already, and whenever you double click an application icon, the program, quote unquote, will run. And technically in operating systems, when a program is running, is actually called a process. So after taking ComSci 125, you should now be able to differentiate what a program is and what a process is. A process is defined as a program in execution, and the process execution must progress in, of course, in a sequential fashion, and there's no parallel execution of instructions of a single process. So you've run several processes already. I will not show an example now, but I'll show an example later. So when a program is running, it is in the main memory as required, and it is technically called a process. and it has several parts. We have the text section, which contains the program code, the program counter, as well as the values in the registers associated with the current execution of instruction. There is also a stack which contains temporary data. What types of data? Examples are function parameters, return addresses, and local variables. Then we have the data section containing the global variables and a heap, which is used for a storage area for dynamically allocated memory. So in essence, a process has a lot of components or parts. So a program is a passive entity stored on the disk, basically an executable file. This is a binary file, while a process is an active entity. The program becomes process when an executable file is loaded into the memory, and there are two ways to do that. In GUI environments, you double click an application icon and the process will be created. This is in Windows or in Mac, and you can also use the command line via the shell to execute a program. So one program can be several processes. Okay. So I guess it is best if we show an illustration of this in an actual operating system. So let's start with Linux. Okay, so we have let's go to process folder. So we have this example code. So as you can see, this code simply, you can see some global variables, int x, uninitialized, int y, initialized to 15. Then we have the main function with two parameters, the argc, the argument count, and the argument vector. Then you have a local variable, a pointer variable, int pointer for values, and an integer local variable I. Then we have values here in which it points to the memory allocated using malloc, and then this memory allocated area, the values are assigned to these locations, and then accepts some input and then exits. So this is the source code. Right? And in the previous chapter we discussed about linkers and loaders. So today we're going to show that how they work. So first we compile this to, so this is the source code. The source code is of type an ASCII text file. Now once we compile this, or we build this, then we check the file type of simple.exe, we will now see that this is an ELF LSB shared object file, which is actually an executable, and then we run it. Simple.exe, it will seem to halt, but you need to type in some input like hello, press enter, and the program will exit. Okay. So going back to our slide, so the program is the passive entity. So in the previous example, simple.exe is the passive entity. Now how do we turn that passive entity into a process, into an active entity? So we execute this. So as mentioned, there are two ways to create processes, either by using the command line or double clicking an icon. So in this example illustration, we're going to show it using the command line. Okay, so let's run simple.exe. So it's waiting for some inputs. Now on the bottom terminal, we can type ps just keep it simpler, ps minus a grep simple.exe, and you will see that there is now a process that represents this simple.exe. So remember, in an operating system, normally processes have an identifier or a process ID, and in this case, this process ID of this simple.exe is 3143. Okay. So we only have one simple.exe. Now if we stop this process and then we check again using the ps command for running process, the process is no longer shown because it has terminated. Now let's run multiple instances of this process to illustrate that indeed. Let's try to run 3 instances. So it will appear as if nothing happened, but these processes are actually running in the background. If we go to the bottom terminal, then we use ps again to look for the processes, and you will see that we have 3 processes with different process ID that originated from the same program, simple.exe. So this is what we mean by this. Right? So the program becomes a process when it's loaded into memory. And one program can be several processes. So I'd like you to remember that example. So how do we kill this process? So the ampersand here, as you already know in the shell, puts the process in the background. So we can use the fg command to put a process in the foreground. So we have, let's go to this. I'm running this over the network, so you'll see really some performance degradation. I think I messed this up. So we are back here. We can use the fg command to put a process in the foreground, and then let's type ps, and then let's see which process was killed or was stopped. So the one that we ended was 3152 because we use fg1. So if you want to put this process in the foreground, you can use fg3 and then do something, and then we only have one remaining process, and we can use fg, and we have here the last simple exe process, and then we've killed everything, so there is no more simple.exe process. So that's an illustration of the discussion in the slides. Okay, so let's proceed. So when a program is running, it's a process. Now, how does it appear in the main memory? In this slide, it is described the different parts of process, and this is actually called the memory layout of the process. You have the lower end and you have the higher end. So you have the text section, the data section, the heap, which grows upward, and then the stack located at the top, high memory area, and it grows downwards. So probably you've discussed this in ComSci 131 also. So here we have an example program, which is what I showed you a while ago, and the arrows represent where the information from the source program is placed in the memory of a process when the OS allocates memory for a process. So the parameters, actually the command line arguments, are placed right after the stack, and the local variables are placed to the stack. Then we have a dynamic memory allocation call. So this is placed on the heap. And then we have an initialized global variable. This is placed in this area. And then an initialized global variable placed in their area, in this area. And the instructions, the assembly instructions that represents, this one is a function call, and the instruction for this, for the loop, are placed in this memory area. So how do we view this in a running process? We can actually use a debugger to do this. So let's debug that simple.exe. And let's examine the okay, so we set a breakpoint to the main. And we click this as main. So this is the instruction for in the main function. So you see here instructions like push, move, sub, and move EDI and RSI to some memory location. And you see here the call to malloc. This is the instruction. And you have a jump instruction here, which is probably for the for loop. Okay, so if you look, you can look at the properties of the process by looking at using the command. We have to run first the process. So after setting a breakpoint, we run the program, so it will create a process. And using the command, the gdb command info proc status, we will be able to see the information about the process, like the process ID, process 3204, and we have the name of the executable and other information about the process. So the command is info proc status. Then if you want to look at the memory for this memory allocated for this process, we can use the command gdb command info proc mapping. So this will be displayed. So you see the different areas of memory associated for this process. So you can see the stack at this high memory area, and you have, this is probably the text section, this is the initialized data section, and then we have the uninitialized data section, and then we have these shared libraries loaded. We can't see the heap, right? There's no heap here, no indication, but we have the stack. Now how do we show the heap? So let's take a look at the disassembly of the code. As mentioned also in the slide, we have the program counter and processor registers. So we can actually view the values of the program counter and the registers by using the command gdb command info registers, and you can see the values of the different registers here. The program counter is actually the RIP. In the x86, the program counter is RIP, register RIP, and you can see that the value of RIP is this one. And if we disassemble, you will see that indeed this is the next instruction to be executed for this particular process. Now we don't, as shown earlier, we don't see the heap memory area for this process because we haven't executed the malloc call yet. So we can do this by executing some of the instructions. So let's say if we run ni +2, okay, and then we disassemble, you see that the RIP or the program counter moved 2 instruction. So if we want to go to this point, let's say ni 1, 2, 3, so we can do that. Ni +3, and then we're right before the call instruction. So if we look at the memory mapping, we still don't see the heap, so we execute a few instructions. So we've now called malloc, so it's time to check if there is now a heap in the memory mapping, and you will see now that there is a heap in the memory mapping of this process. Okay, so we can continue the execution until the program ends, and the process exited normally. So I hope that demonstration gave you an idea of what processes are and the information that contained in the process memory shown here. Now, processes also have states. I forgot to show you some examples for Windows. So let's take a look at Windows. I think I already done the examples here. So we have so this is the same code, C code for the Linux example. We're going to compile this. simple.c, and then when we type simple.exe, so the program will stop, and then it will, after inputting something, press enter, then the process will eventually end. So we can see this in Process Hacker. So let's run this. So it's waiting for the input, and then if we run Process Hacker, we should be able to see that simple.exe running. So let's take a look. Can you see the simple.exe process here? Right. So we have the command process, and then we have the console host process, and then this is our simple.exe process invoked using the command line. Now we can view the properties of the process, and for example, look at the memory as we did in Linux. So you see here the memory mapping for this process. So remember that this is an entirely different process from the Linux process. Although they have the same C source code, they have different executables, binaries, and their process structure is also different because the process structure depends on the operating system. So you see a different mapping here, but you can probably see okay, so you can see here the heap, okay, similar to the one shown in Linux, and you also have the stack here. Okay. So you have the PAB structure here, which is equal to the PCB structure in the lecture. Okay. So normally processes have a parent-child relationship. As you can see in this hierarchy, simple.exe is a child of command.exe. Okay, so that's the example for Windows. So to terminate the process for the Windows, you simply I think I lost control of the mouse. Okay, but anyway, let's proceed to the lecture. So a process also can be in different states as it is executing, and there are 5 general states of a process. A process can be in the new state when the process is being created. It is running state when the instructions are being executed. It can be in the waiting state when the process is waiting for some event to occur. It can be in the ready state when the process is waiting to be assigned to the processor. and terminated when the process has finished execution. So this is the state transition diagram for a process. So when a process is created, it will be admitted, and once admitted, its state will become ready. Then when the scheduler selects that process to be run on the CPU core, its state will be running, and then it may be interrupted, so it can go back to the ready state, or once it's done with its task, it can exit and eventually it will be terminated. Now, while it is running, if the process performs an I/O operation, it will go to the waiting state, and then once the I/O is completed, it will go back to the ready state for the CPU scheduler to select it to become a running process again. Okay, so if you have a single core, then only one process can be in the running state. But if you have multiple cores, it's possible to have multiple processes that are in the running state. Okay, so if you're going to write an operating system, normally you have to define a structure called process control block that describes the abstraction of the process. This is usually a struct definition in C, and in Linux it's actually called tasks, right? Or task control block. In Windows, I think it's called a thread execution block or something. So what are the fields of this process control block? We have the process state, the program counter, so we define the different states, the CPU registers, the CPU scheduling information, priorities, pointers, memory management information, accounting information, CPU use, clock time, and many other accounting related information, and I/O status information. So there are a lot of information contained in a process control block. Let's take a look at an example. So let's go to the connection is quite slow because I'm actually accessing this machine from ICS. It's a remote server. I'm just connecting via VPN. So because I don't have a high-end machine for my virtual machines, so you see sometimes that the VNC freezes. Okay, so I no longer have control. So let's take a look at ICS OS. cd ICS OS. It's the source code. Okay, so let's look at the definition of the process structure or process control block for ICSOS. So you can see here the different access levels for the process control block. This is for inter-process communication, some parameters, some constants, some definitions. Let's look at the structure definition. Okay, so we have here a node for the memory management. So we have the pointer to the virtual address and the pages associated with it. Discuss that later. Okay, so this is not the process control block. So this is the structure used for context switching. We will discuss context switching later, but when a process is moved out of the CPU, the state of that process is stored in this in x86 is called task state segment. So it's a data structure that contains the registers, the values of the registers for a given process. So this is actually hardware specific. So if you are using an ARM processor, writing an operating system for an ARM processor, this will be different. Okay, so this is the process control block. So you have the task state segment I mentioned earlier. If the processor is using a floating point unit, okay. So these are the fields for the process. So page directory location, the process ID, okay, the process owner. In multi-user operating system, we have some protection mechanisms, and you should have an owner. Okay. The name of the process, the current working directory, the access level, the priority used for scheduling, the status, okay, the child weight, we'll discuss that later, and other information about the process. So a process will have a pointer to its stack and a pointer to the memory location, memory information associated with the process. And you also have the other parameters for this process, for a particular process. And normally a process has a standard input and standard output, so you have something like that also here, and many other information describing a process. And normally the process list maintained by the operating system is a linked list. So you will see here pointer to the next PCB and pointer to the previous PCB. You'll have an experience navigating to the source code in the later part of the semester. We have specific labs for ICSOS. Okay, so that's process control block. Threads. Okay, so far process has a single thread of execution like the one I've shown, simple.c, and it's also possible for a single process to have multiple program counters. So let's say you have a process here Normally, it will have a single thread of execution specified by program counter 1. Now, if we have another program counter 2, we can have another thread here. Okay? And this will allow multiple locations to execute at once. So in Java, probably you've done some thread programming. So if you have multiple threads, you must then save the storage for the thread details, and should have multiple program counters in the PCB shown here. And we'll discuss threads in the next chapter actually. But remember that it is possible, as you've seen already in the Windows example, for a single process to have multiple threads. In Linux, we have if you look at the source code of Linux, they have the task structure, which contains this information, which is very similar to the one I showed a while ago for ICS OS. So you have the process ID, the state of the process, time slice used for scheduling, the parent, the children, pointers to the children, list of open files, and the address space for this particular process. So these are just a few of the fields in the task struct in Linux used to represent processes. Okay, the next one is process scheduling. So there is usually the operating system performs some scheduling, so that if you have, in a multi-programming system, if you have a lot of processes, you can schedule each of these processes. So for example, we have P1, and then P2, then we have P3, and this is our CPU. We only have one core. Let's just use core. If you have, these are all in the memory. Okay. So remember that processes, assuming that all of these processes are in the ready state, so they are waiting for the core to be, waiting to be executed on the core. So this is called the ready queue. So this is already executed, and then the idea of process scheduling is it will select one process. Let's say it will select P1, then after a while it will remove P1, and then it will set P2 to run on the core, and after a while it will remove P2 from the core, and then it will run P3 on the core. So that's the process basically, and that is done by the process scheduler in the operating system. The goal is to maximize CPU use and to quickly switch processes into the CPU core. So whenever you change the process running on the CPU core, that will actually cost some time. So that switching must be efficient. So in order to do process scheduling, the operating system maintains several scheduling queues, and one of which is the ready queue, as shown here. So you have a linked list of processes that are ready to be executed on the core. There are also wait queues, which is a set of processes waiting for an event, say I/O, and these processes will migrate from one queue to another. For example, we have this queue. So let's say we have process 1 is waiting to read data from the disk, so it will have to move to this disk queue or a printer queue or something, some I/O device. And the OS, the kernel, actually will have a module for scheduling these processes. So here's an example, actually just almost the same as the one I have here. So we have different PCBs, and this is the wait queue, this is the ready queue. So this one has a pointer to the head and a pointer to the tail, if you recall in ComSci 123. And we can also have this view of the process scheduling. So we have the rectangles represent queues, and the circles represent some events. So the ready queue, from the ready queue, the process will go to the CPU. Then while executing, that process performs an I/O request, and thus it will wait in the I/O queue, okay, and then go back to the ready queue. Or while a process in the CPU, its time slice expired, because normally in operating system there is a set amount of time for it to run on the core, so it will expire and will go back to the ready queue. Or if the process forks or creates a child process, this is what will happen, and it will wait for the child to terminate and then go back to the ready queue. Or it can wait for an interrupt. Let's say it issued an int instruction, so it issued a system call, for example, so it will wait for an interrupt and then move back to the ready queue. So the cycle continues, so the process will move from one queue to another. Now the term context switch, this refers to the time when the CPU switches from one process to another. So this is the timeline to illustrate that. We have a process P0, so it's currently executing. Then this process P0 performed issued a system call or called a system call. So the operating system must execute. So it will save the state of this process 0 in the process control block 0 so that it can go back to it later. Then after some time, so at this point, while executing the system call, process 1 is doing nothing, it's idle. So after the operating system determined that instead of running P0, it decided to run based on some scheduling criteria. It decided to run PCB1. It will reload the stored state of P1, which is PCB1, and then transfer control to process P1. The OS will transfer to process P1, then it will begin executing. Now at some point there is a interrupt or system call in the execution of process P1. Then PCB1, the state of computation of P1 will be stored in PCB1, and then the kernel or the OS will perform the syscall. After the execution, it can it can choose to transfer control to process 0. So it can be a system call or the timer interrupt. So let's say the timer interrupt happens, so the OS kernel will take control. So the switching is called the context switch. The loading of the PCB to the actual register of the processor is called the context switch, and it takes some time to do the context switch. So when the CPU switches to another process, the system must save the state of the old process and load the saved state for the new process by a context switch. So the context of a process is represented in the process control block, and it is pure overhead. So it's simply switching values, actually copying values from the register to some memory location, data structure PCB. So it's overhead. So the more complex the OS and the PCB, the longer the context switch. Modern hardware actually provides some support for context to improve context switch time. Example of that is by providing multiple sets of registers per CPU, which allows multiple contexts loaded at once. Okay. So that's context switch. And in mobile systems, okay, some mobile systems only allow one process to run, others are suspended. So there is a state called suspended, or at least process in the ready state. So what they did is to just use different types of processes. We have foreground process and background processes. For Android, we also have foreground and background processes, and sometimes we call them the background process services, and these services still run in the background even though the process is suspended. For example, Spotify. So if you listen to Spotify, so it has a service that runs in the background so that you can still listen to music while doing some other task on your Android device. Okay, so we'll stop here, then we'll continue to the next video later.